Hello and welcome to today's presentation. Today, we are going to present our work with the design and analysis of a smart grid system in a remote community in Atlantic Canada. Me, Anila Chakma, and my group mates Manush Chandra Haldar and MD Majedur Rahman will try to explain the work in detail and answer any question you may have. So, electricity is what drives the modern world, and the grid system is what keeps it in motion. The basic structure of electrical grid system consists of generation, transmission, and distribution. The electricity is produced from the generation station and then followed by a transformer and transmitted to wherever the transmission line is connected and wherever we need the electricity. Electricity with different voltages is transmitted through the transmission line to the final destination, and that's how we actually get to use it in our desired location. Okay, now coming to the background of our project, why we are working with a smart grid. Well, before discussing that, let's see what the report says about the power outage in Canada. According to the IT World Canada's report, more than 400 power outage is common in Canada every year. And the reason behind this power outage is can be a lot of different issues, and one of the main issues is the climate change that has been influencing the extreme water pattern throughout the world, which is the reason behind tons of different natural disasters, including ice storms, hurricanes, tropical storm, wildfire, and many tornadoes. With disaster like this, the electrical power infrastructure becomes very vulnerable and can hamper the lives of that certain area for a long time if the damage has not been controlled on time. The research paper by shows that 41 of the 57 major power failures in US and Canada were due to heavy snowstorm between the year 1964 and 2009. And with the climate change, the number is going up. So we need to find some easier ways to control this imbalance and have better control on the electrical power infrastructures. So now we understand why we need a better control on our grid systems. And from there, the solution modern technologies have given us is the smart grid. What is a smart grid? As discussed before, the electrical distribution has three parts: generation, distribution, and transmission. When one of the parts is affected, the whole system can fall apart and needs manual fixing to get back to the active status. With technologies, a smart grid is an electrical grid which includes a variety of operation and energy measures that will meet the high demand of electricity and can manage the increasing complexity and needs of electricity in the 21st century. So basically, a smart grid can understand the demand and supply through it and can follow when things go wrong, when a power outage happen, and take steps on its own to handle it. Here we have prepared a table that will give us a better understanding and show the difference between a traditional grid with the smart grid. At the beginning, so the system, the way smart grid work is mechanized way, and it's mostly done manually, where smart grid will be total digital and have the ability to make decisions on itself. And then the communication through the smart traditional grid is always one way from the main generation port to the consumer, but the smart grid can be two-way and has a real time connection between them, and that makes it more easier for the consumer and to move to the renewable energy sources. And as it goes, as it has a two-way communication system, the smart grid power generation can be distributed and can connect different renewable sources at the same time, where traditional grid is just one centralized option. And the data collection, traditional grid does not have a large volume of data involved in it, but the smart grid does. And with the data, it increases and it understands what's the demand and try to deliver that. And with the automatic sensors and monitor use, it can be easier to monitor and control with the smart grid. Well, recovery from different power outage or different emergencies, the smart grid has automatic option to work with it, and but the traditional used to be manual. And with the security and privacy, traditional grid is not very concerned as it is manual, but smart grid does have a little vulnerability when it comes to security and privacy issues, but we believe that our technologies can take care of that. Response to emergencies, smart grid is fast and intelligent with its data and stuff and knows how to react and how to get back into the active status as soon as possible. The consumer involvement, which is very important, and with the smart grid, consumers have vast choices to choose how they want to manage their energy and how they want to connect it to it. And with the traditional grid, it's not very much. Okay, from there, to understand the smart grid better, we have prepared a block diagram. So within this diagram, at first we have the generation part, and the best thing about smart grid is it's compared to, as mentioned earlier, compared to traditional grid, it can connect multiple energy sources into one generation facility. So let's say traditional power generation plant and then different renewable sources. It can all be connected to a smart grid. And from there, let's take a look at the transmission and distribution block. So here we have the power of grid automation, intelligent substation, which will understand the demand and sort the power energy towards that. And then smart switch distribution and automation makes it way easier, and then remote control and condition monitoring. So by that, it will help have accessibility remotely. So, and if anything goes wrong, so it will be able to revive and become active within a easier time than compared to a traditional grid. And finally, within the residential, industrial, and commercial system, when it is delivered to the designated area where we are going to use the electricity, it has different kinds of distribution systems. So we can have residential distribution systems, industrial or commercial distribution systems, depending on the what is the demand and how we can improve it. And then we have the option of smart metering and advanced metering infrastructure, which gives the consumer the control and better understanding, and they can manage their use or consume electricity with more awareness. Energy storage, mini energy storage, that can also be put together. And as we are moving forward, electric vehicle becoming more and more popular around the world, and smart grid will help understand that if a house or if a residential or commercial area needs more sources for electric vehicle charging. Also, distributed energy management system makes it easier, and as we work to work with sustainable and smart buildings, having a smart grid will make that option very much easier. Okay, after getting an idea of what smart grid is, let's see how's Canada doing with the with the implementation of a smart grid into the market. So, in the Paris Agreement, Canada has taken a goal to reduce its greenhouse gas emission by the year of 2030 to the level of 30% below of 2005 levels. And also within the same timeline, Canada wants to produce its 90% electricity from the renewable sources. And what better to connect all the renewable sources with the main grid using a smart grid. And here we have a presentation, a graph to show the 758 million dollar funding is going towards different projects which mainly focus on energy storage, microgrid, grid monitoring and automation, electric vehicle integration, distributed energy resource management, and demand management. From here, we can see that the grid monitoring and automation connected with the distributed energy resource management has the most project value with it. Also, a microgrid comes in the second place. And also with related to this, the Canada market is also preparing for this high demand of electricity in future, and they are taking a lot of economic incentives to push it towards the goal 2030, and the smart grid will become a friend to that. So that is what I have I had to discuss with the literature review and have a better understanding of what is going on in the study. And now my other group mate will describe the methodology and more. Thank you.
Thanks, Anila. So, before starting to work with smart grid, there were a few key aspects which we considered. So let's take a look at them. So the first was power system enhancement. So part of the goal of smart grid is also to enhance the experience environmentally as well, comparing to the regular smart grid. So this factor provokes the policymakers to involve renewable energy in the smart grid. Policymakers assume that greatly expanded use of renewable energy resource in countries like, say, United States will help to offset the impact of carbon emissions from thermal and fossil energy to meet uncertain demands and to some extent increase reliability of delivery. Then next aspect of a smart grid is testbed. So as we know, a testbed is a platform for conducting rigorous, transparent, and replicable testing of scientific theories and new technologies. The term here is mainly used across many disciplines to describe experimental research and new product development platforms and environments. Here, for smart grid, the testbed will be the hub that brings together separate pieces of technology and energy delivery to produce a more integrated grid for the future. Then the third one is environment and economics. So, as stated earlier, smart grid is all about enhancing the experience from the basic grid. It will focus on the environment by considering renewable energy and also will assist on cutting the cost by technical feasibility and customer involvement. The fourth aspect of smart grid is computational intelligence, which is the term used to describe the advanced analytical tools needed to optimize the bulk power network. The toolbox will include heuristic evolution programming, decision support tools, and adaptive optimization techniques. And last but not the least, communication and standards. Now, since planning horizons can be short as an hour ahead, the smart grid's advanced automation will generate vast amounts of operational data in a rapid decision-making environment. New algorithms will help it become adaptive and capable of predicting with foresight. In turn, new rules will be needed for managing, operating, and marketing network. big part of a smart grid is the integration of renewable energy. Renewable energy enhances the overall features of a smart grid. Renewable energy source outputs can be controlled distantly as well. Moreover, additional generated power can be redistributed based on demands in the network. With renewable integrated smart grid, even electric vehicles can be facilitated as well, and energy can be stored as a battery packs for EVs for instant recharge. And it's all about contributing to the ultimate green energy. However, after considering numerous factors like cost, feasibility, and natural impact, solar energy was chosen as the primary renewable source for the proposed grid. So, as we know, solar energy is abundant in nature and doesn't emit anything lethal to the nature. And as the grid would be designed for Atlantic Canada, using hybrid photovoltaic or thermal, the additional thermal energy can also be employed for household heating, and this feature would be beneficial especially during the island mode. Now, let's take a look at the proposed designs of our smart grid.
So referring to the design details that will be implemented for the smart grid of a rural community of Canada. First, we have selected a 100 kilowatt photovoltaic array which is connected to a 25-volt grid via a boost converter. From the simulation, we can see that a PV array is connected to a boost converter and is connected parallelly to a MPPT controller, and then it is connected to a voltage source controller which is supplying to the utility grid itself. So referring to the PV array block, we can directly control the number of strings that are connected to the photovoltaic power generation modules. We can also control the maximum power level, open circuit voltage level, open circuit current level at the maximum power point, irradiance level, and the operating temperature from the PV array block. We can also select the commercial PV array from the library itself. For this simulation, we have considered a SunPower SPR 305E type module, which is widely available in Canada. Furthermore, we can also see that the PV array is parallelly connected to the MPPT controller, which can track the maximum irradiance produced from the sun, and then it is connected to a boost converter 5 kilohertz 500 volt. The boost converter is directly supplying to the 3 level 500 volt 60 hertz bridge rectifier via a DC link, and as you can see here, the DC link or the DC link is also connected to the 3-level voltage source controller, parallelly. The main function of the voltage source controller is to control the DC link and the current output. From the voltage source controller block, we can see that it has two loops. First loop, the external loop is controlling the DC link at 500 volt, and the internal link is directly supplying the current to the utility grid itself. The 3-level bridge rectifier is also connected to a inductance bridge, which is controlling the harmonics generated from the power output. It is also connected with the 10K VAR filter to directly remove the harmonics generated, and it is supplying a pure sine wave for the utility grid itself, so that the voltage and current levels are constant throughout all time, and it can supply the utility grid at distant transmission lines. So we will have a direct look at the voltage and current level that is supplied to the utility grid from the next slide. Now from the PV array output block, we can observe the irradiance, operating temperature, mean power produced, mean voltage, and the duty cycle from the simulation. The simulation has been taken for 2.5 seconds, and as you can see from the graph, the photovoltaic module reaches up to the maximum power output from its generation with an operating temperature of uh, 25 degrees. The irradiance is considered 1000 watt per meter square. The output of the power is close to maximum and is producing the maximum power with minimum loss. The mean voltage is more than 300 volts because the open circuit voltage, and it fluctuates through time and then reaches a steady state value of near about 220 volts. The duty cycle is 0.5 at the beginning, but decreases to 0.45, and then it fluctuates over time. The fluctuation is because of the MPPT controller, which is tracking the maximum irradiance from the sun. The MPPT controller basically generates a signal which changes the duty cycle to produce the maximum power output at a minimum loss. So the simulated PV array is generating maximum power with a minimum loss for our smart grid. Now let's have a look at the output voltage level of the converter. The converter begins to operate at 0.05 seconds because of the step time provided. So as you can see from the graph, the first few lines before the operating time is because of the open circuit voltage level. So when the converter begins to operate, it operates in three different levels. The output of the voltage is similar to the voltage output of the utility grid itself. As you can see from the graph, that the voltage converter converts the DC voltage level to similar or to that of a sine wave, but after using the harmonics filter, it can generate a pure sine wave, which we will see from the next graph itself. So this is the final representation of the voltage and current measurement taken from the simulation. We can see that this simulation is capable enough to generate pure sine wave for each phase levels, and therefore this simulation can be used to implement a successful smart grid for a Canadian remote community. Now, a small-scale smart grid simulation has been created so that we can implement it in the future to generate a smart grid simulation for a remote community. As you can see from this simulation, the small-scale smart grid consists of a power grid, pole-mounted transformer, solar panel PV array output that we have seen from the last simulation, a battery controller, and load of three houses. So the battery controller is compatible to store electricity when excess power is generated from the grid or the solar PV array, and supply power at the same time when there is shortage of power, or the grid is disconnected from the remote area, or the solar panel does not have any sunlight hours. It is a simplified model of a smart grid simulation that we are going to use in the future to simulate a smart grid system for a remote community. So to conclude, we have seen that the simulations we have presented in this research study were successfully able to implement an intelligent controller for a PV array and a small-scale microgrid to power up to three houses. In the future study, we're going to use these simulations and our work to generate and design a smart grid for a remote community in Canada.